we continue with the calculation of the hyperbolic arrival trajectory. So before we already calculate about the hyperbolic transfer orbit, so next towards the final destination of this arriving circular parking orbit, first, first we are about to find hyperbolic arrival trajectory. So here on the screen is the example and the equation that we're gonna use for our calculation. And oh, I'm sorry, on the bottom left screen, so it still shows that the VC1 AH1, actually it is VC2 AH2 and so on. So the main concept is the incoming satellite, which is the Voyager 2 that we are using, will arrive at the final destination of the parking orbit around the Jupiter orbit. So we're going to find the velocity of the incoming trajectory and the velocity of the circular parking orbit of Jupiter. So that is the main concept of we're we're gonna find. So we're gonna calculate the value of A, which is the semi-major axis, the eccentricity, the velocity VPH2, VRPH2, and so on. Okay. Then the second concept is the calculate the maneuver parameter between aerocentric object orbits. The V rifle is the differences or delta or the VC2 minus VH2, which is the velocity of the circle parking orbit minus the velocity of the incoming trajectory. Then we will have the eccentricity by we will find the theta by using the inverse cos of 1 per eccentricity and the value of alpha. Okay, so let's proceed. We already have the V infinity, so we can find the energy characteristic of C3, which is the equals to V infinity square equals to 29.128 kilometer per second square. So here, same as before, we're going to use point as to point out where the decimal and the comma as the thousand. So next, we find the parameter of R of our semi-major axis and the E or eccentricity using the equation like the slide below before. So we can find the semi-major axis and the eccentricity as the screen. That we have semi-major axis of minus 4.346 times 10 to the power of 6 kilometer and the eccentricity of 11,663.325 kilometer. Then we can find the parameter of hyperbolic arrival velocity and radius as shown below. And we can find the finding circular parking orbit parameter of RCS or equals to RPH2 and VCS. So we have the maneuver parameter that the delta V rifle of minus 13.705. The minus here means that the VC2 is much smaller than VPH2. So the thruster have to reduce. The thruster have to reduce the satellite speed. So in order to the satellite to be able to orbit around the Jupiter, and we can find the radius of the circular parking orbit and the theta of arrival. Okay, next we use Raman orbital transfer again to calculate the sync time in heliocentric orbits. So why it is so important for us to calculate the sync times and sync position of the destination satellite? Here's the concept. Here is the concept. So on the screen we have Mars as our example, and so our mission recap is the Voyager 2 with its rocket will launch on Earth, then ejecting into the parking orbit, waiting until certain moments, then it injects again, the thruster turn on and bring the satellite into the final destination. So in order to time the thrusting completely, we have to calculate to approximate the position and time of the arriving position beforehand. Here we have to determine here in this example we have to determine the position of MO, which is the position of planet Mars. In this example, we're using Mars. We are using theta. So we are so when the Mars have a certain theta of the orbit, that is the time that we launch the satellite from the parking orbit. So the satellite will arrive in the Mars at its perfect position. So here we have ET or the transfer origin parameter of period, which is the 556.93 day, and we have the TOF. TOF is time of flight equals to half of the period, and we also have the Mars orbit parameters of PM or Mars period and half period of Mars. We also have the TMO minus TMA, means it is the time of flight. Then time of it is the time of flight of transfer orbit parameters. So yes, and the TMP minus TMO, which uh we subtract the half of period of the Mars itself and the half of period of the transfer orbit parameter. Then from the calculation before we proceed to find the EPO, we have the EPO to find the theta zero of the planet. So here is the concept. We already have the TPO from the explanation before, that the half period of the destination planet minus the half of lifetime of the satellite. So we also have the NM, that's from the equation of EPO minus little e, or we will call it eccentricity, times sin EPO equals to TPO times NM. So because we already have the TPO and NM, that value becomes constant, and the eccentricity of the destination planet, which is in the example is Mars, is also constant. So from that we can use those variables to find the EPO. But the problem is one EPO is in the sinus. So as we know, some certain of degrees, some value of degrees produce say the same value of trigonometry. So we're going to iterate it. And how to iterate it? So first, we have to iterate it roughly in order to get the closest value near to the value of our want. Then we can use many different methods to find it. Okay, let's jump to the calculation. Revolution for orbital transfer. We call PT using the period equation. We have the value of period of orbital transfer of 2,114 days, and the time of flight is the half of the period. And since the revolution of Jupiter is 4,334 days, the launch timing is TGO, and TGA equals to 1,057 days, and the TGP, TGO equals to 1,110 days. Next, the calculation of Jupiter position when Voyager 2 is escaping from its parking orbit, initial parking orbit around Earth are the TPO equals to 1110 days, and NG equals to 0.001449 radian per days, and So thus we can calculate the TPO times Ng equals to 1.609. So from the equation of TPO times Ng equals to EPO mean minus eccentricity times sinus EPO, from the value of 1.609, we need to do the iteration to find the value of E. So we do the initial iteration to roughly find the closest value of EPO, which produce the TGO to produce the TPO times Ng of 1.609. So the closest but still below our goal value is the EPO of 1.65635. Okay, from the rough iteration, we have to iterate it again using search method to find the exact value of EPO. There are so many iteration method. Just here we are using interruption iteration method, but you still can use many methods like second method, bisection, or many more. But the thing is, if if you use different iteration method, fortunately, interruption is one of the simplest one, and very fortunately, it produces the one of the most exact approximation value. So here we have the xi. It is the initial value of our initial iteration value, and xi plus 1 is the iterative value that we have to use it to the next iteration, and we have the value of f and fx. The fs we have from the function of the EPO minus eccentricity sinus EPO minus TPO times Nj. So if we can produce all the value of f equals to 0, it means that the EPO minus Esin is equals to the TPO times Nj. So the Newton-Raphson iteration method itself is the xi plus 1 equals to xi minus f divided by fxf. So here we see and the from beginning of the third iteration that we already have the value of f of 0. It means that because of the value of f is 0, it means that from the graph we already reached the roots. So we can see that the xi already equals to xi plus 1. So that is the value. So from the value of E, which we calculated before, we can find the theta, which is theta equals to 97.729908 degrees. Then we have to calculate the proper requirement. So uh, here our calculation is the reconstruction of the Voyager, but in reality, if you are calculating for incoming mission, of course you will use many more assumption and the safety factor. But here we use the recap data that we get and our assumptions. So here the main concept is delta V total is V escape plus V arrival. It means that it is the example for the transfer orbit only, but if we are going to calculate the from the Earth to the parking orbit and from the transfer orbit into the final transfer orbit, we still can use this, but just change the delta V escape and delta V arrival. Okay, next. So from the equation before, we already have the value of launching site into parking orbit, the escaping from into the parking orbit, and arriving at the destination. Thus, we have to compare it from the data. So here, stage the differences here is actually that because of our assumption and our we don't use any course correction, so on. So yes, that is for explanation for this. And thank you very much.